Well, good evening everybody, or good afternoon whenever you're going to be watching this video. So I guess right now it is Monday evening as I'm making this video, but this is going to be just a video that is going to replace our normal Tuesday class because I will be in a faculty senate meeting tomorrow or today whenever you're watching this. So I won't be able to do a live video on that day. So I'm just going to have this video replace our class. So we last left off doing prefix code using Huffman, sort of Huffman's algorithm. And the idea was we wanted to sort of compress each letter using as few number of bits as possible. So the idea was that each letter in ASCII is 8 bits of ones and zeros, and we're able to compress using less number of bits and still be able to produce a file and be able to have a bunch of ones and zeros and be able to decipher which letters we're trying to actually use. So the whole idea is this is mostly for compression type algorithms they use this for. So when you finally have our decision tree, which we computed last time, every left branch would be a 0 and right would be a 1. So going from the root to a leaf, we can actually construct every single code. So A would be a 0, C would take that right branch, so it's 1. So we would go ahead and choose 1, 0, 0 for C. And then we'd have 1, 0, 1 for B, and so forth. So having these, the whole idea is that they are prefix code, which means there's no subsets over here. So we can't, there's no way to overlap any of these because we have 1, 0, 1. We don't have a 1 and then a 0. So there's no way we have no subsets because A, which is a 0, the 0 is not a subset of any of these strings over here. 1, 0, 1 is also not a subset of any of these as well. None of these are subsets of each other. So if we were combined together, we'd be able to easily replicate the letters. So for example, if I have something like 1, 0, 1, then 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, let's say 1, 1, 0, 1, we could easily take this string and decipher it and get our letters out of it. Because when we have a 1, then a 0, then a 1, we know this has to be B. And we know it because there's no scenario here where we're going to have a 1 by itself or a 0 by itself where it gets confusing. Because if you have a 1 then followed by a 0, I know we have A as a 0, but there is no like 1 standalone and 0 standalone. So it's not going to overlap. None of these overlap with each other. So if we see a 1, there's got to be one of these 1, 2, 3, 4, 5 possible letters. So the whole idea is just that we can sort of take these and construct this. So we have 1, 1, 1, 1. This has to be the letter D. Then a 0 has to be an A. Another 0 has to also be an A, because if the first character is a 0, we can automatically say it's an A because there is no 0, 1 in this set of characters. So the whole idea is that we're not going to have a mistake where we're going to have, well, there's not going to be any ambiguities here. We can easily decipher this. So now if you have a 1, then another 1, then 0, 0, then this has to be F. There's nothing else this can possibly be. We can't, there is no 1, 1, or there's 1 by itself, or 1, 1, 0, and then 1, 1, 0, 0. There is no case like that. So we can see here, there's no way we can make any mistakes here. A 0 by itself has to be an A once again, and a 1, 1, 0, 1, it's going to be E. So we had the following letters. So using these digits, these bits, we can actually expand them to letters. So the whole idea is that we don't have to use 8 bits for every single letter. We can use these smaller amount of bits to represent these letters in a string. So it's a way to compress a file into a small number of bits is the idea. So basically for this assignment, this example, you'd have to go ahead and do the same algorithm on maybe on a different set of letters, different frequencies. Then we'll go ahead and given the following string, decipher it into letters. So I would tell you for a homework assignment, you'd have maybe the following scenario. Here's going to be your set of letters and frequencies. You have to go through all these steps one by one to get this final decision tree. And then given the decision tree, give me the prefix code for each letter. And then given this set of digits, ones and zeros, set of bits, basically just expand and decipher it into the actual letters. So this is kind of the use of Huffman coding. So that was our first divide and conquer algorithm we actually did. So this one, let's go ahead and go over the runtime analysis of this algorithm next, and then we'll go over some other divide and conquer algorithms. Now, the other ones are going to be stuff you definitely have seen before. So we're going to cover Dijkstra's and Kruskal's algorithms next, but this one was probably not covered in CS302, so I feel good about at least having something that was not in 302, so at least you get something different out of this class. So the runtime for this algorithm. So runtime for Huffman's algorithm. Let's go over the pseudocode for a second to make sense of this algorithm. Okay, so back to our pseudocode. So that right there, PQ equals C, is the very first line we have here in Huffman code. Well, essentially our input will be n, which will be number of letters, and creating using a build heap to create a heap out of this, it will take O of n time to create this. This step will take O of n steps, because every time we insert this, remember we're going to do a build heap, so we have our whole array of all of our letters with our frequencies and do a build heap. So we bubble down from the leaves upward using our build heap operation. There's an O of n runtime right there. Now this for loop is going to run at least n minus 1 number of times, and then within each body of this loop, well, this work right here takes O of 1 time, constant time, to allocate a node. Extracting a min from a binary heap. So this will be using this extract min. This PQ is going to be priority queue. It's going to be a binary heap. This will take O of log n time to get a min, O of n log n time again to get the min. This will be O of 1 time to do this simple addition, and O of log n time once again to insert into our structure. So since we have a heap, we always remove 2 elements. We'll take O of log n plus O of log n, and then plus O of log n at the very end to insert a new element into our priority queue. So then we're going to do this work n number of times. So the runtime is going to be, in fact, O of n log n. So I guess there's nothing more. I could have actually written this out more in detail, but that's really is the runtime. So we do this n number of times, and each inner loop, this for loop right there, we just simply do 3 operations on our heap, 2 deletions, 1 insertion. So it's O of log n, O of log n, O of log n. We do 3 O of log n's, which will be overall O of log n, and we do n number of times. So I guess that was kind of anticlimactic because, well, maybe I'll write some stuff down over here, I guess. So we initially run build heap on the letters using their frequencies. That'll take O of n time. We have n letters we're going to be doing this with, and then we're going to basically run a loop that I guess runs O of n time, and the iterations we're gonna do 3 sort of operations on the min heap, each taking O of log n time. So this will overall take n log n times. So O of n to first construct our min heap plus O of n log n. Overall runtime will be O of n log n. Now, I forgot what kind of structure this is, but there's actually a Van Emde tree. I forgot what the actual name of it is. It's actual a certain kind of tree you can use that can get the runtime to be better than O of n log n. But we'll go ahead and stick to using binary heaps. So a binary heap will be used to maintain the next best move. It's obviously a greedy algorithm, and the binary mean heap is going to always pick the 2 best trees to combine together to create more trees. So this divide and conquer algorithm is n log n. Using the min heap is going to allow us to sort of emulate or implement this greedy approach. So that's Huffman's algorithm. Let's go ahead, and I'm just going to just kind of pause the video for a bit now, just zoom ahead. And the next thing we'll go over is going to be Dijkstra's algorithm. All right, so Dijkstra's algorithm. So we're going to cover other shortest path algorithms later on, but our first one we're going to be using is Dijkstra's algorithm, which is it's a greedy algorithm that does shortest path. So the first thing I'm going to do is talk about the following, that it's actually going to be a single source shortest path algorithm, which means that it's going to have the following property where we pick a starting node, and if from that starting node, it's going to find the shortest path from that start node to all nodes in the graph. So it's not going to do all pairs, only just a single start node to everything else. So it's going to be really a weighted graph version of breadth first search. So it's just basically, it's a BFS algorithm modified for weighted graphs. And one thing I want to talk about is for Dijkstra's algorithm, negative edges, so actually if there are negative edges in the graph, so if there are negative edges in the graph, Dijkstra's algorithm will not work. Because it has this greedy approach, basically. So because it's a greedy algorithm, it picks next best move first. If a negative edge is present in your graph, that could be a problem. So being greedy at that point will actually cause a problem. So as long as our graph has no negative edges, it'll work just fine. Now, also in general, if the graph has a negative cycle, then no shortest weighted path exists. This is not specific to Dijkstra's algorithm. This is actually in general. If you have a graph with negative cycle, then there is no such way to get a shortest path. This is actually equivalent to having a perpetual motion machine. So I'll have some type of an example later on. But a negative cycle is almost equivalent to, let's say, if you're riding your bike to go to school, and you want to go to school and you're going downhill to get to school. Going downhill did not cost you any sort of effort. You have a bicycle, you just go downhill, no effort whatsoever. You're going from school back home, it's also going to be downhill. And that's basically impossible. That makes no sense at all. Actually, in fact, in the past, I trolled not a student. I was in high school or junior high then. I trolled a student or a fellow classmate one time by saying something like that, and he was just getting really irritated, getting really mad. He couldn't tell I was obviously joking with him, saying that, yeah, I'm gonna go downhill to school. Well, then you have to go uphill, don't you? No, I go downhill back home as well. And yeah, he just really, I think, like some type of a switch or some type of he short-circuited for a little bit. I think he was catching fire or something, but that was fun doing that. Anyway, so it doesn't exist, a perpetual motion machine. That scenario does not exist either. So you can mess with somebody, but that doesn't actually work. So let's go ahead and now talk about a Dijkstra's algorithm. So basically, a min heap, a binary min heap, we'll use a binary min heap just to make things easy. A binary min heap is used to enable this algorithm to be a greedy algorithm. So it seems like for greedy algorithms in general, like a min heap is kind of the preferred data structure of choice, because a min heap always picks next best move. So it's always the next minimal cost move is always what you want to do. So a min heap is a perfect way of being able to actually perform this. So let's go ahead and now talk about this algorithm. So you're going to have a min heap. You're also going to have a weighted array that stores all the path weights from a starting node to any node in the graph. So basically this weighted array is going to have your solution. So the heap is going to always maintain nodes that are currently in processing, and the weighted array is going to give you, oops, I should have moved my screen down a little bit so you can look at this. The weighted array is going to just basically have your final solution, essentially. So let's go ahead and go over this algorithm. So the first thing we're going to do is let's go ahead and write the pseudocode for this. So it's going to be, I'll put this bullet here, pseudocode. So we're going to call this Dijkstra's algorithm. Actually, I'll call it Dijkstra. I think I'll call it Dijkstra. That's how it is in the book. Then we're going to have G, and I guess we'll have W, and we're going to have S. So G will be your graph, and G contains a set of vertices instead of edges. W is going to be your weighted array, and S is going to be your starting node. Okay. So the first step is we're going to set all, Wi equal to infinity for all I equals 0. For all I equals 0 to, I guess, actually I'll probably write this more generically. So for each vertex I in V. That's probably, I think it's a good mathematical description of this. And then we're going to have a priority queue. I'll call it PQ once again. So PQ, we're going to essentially just insert the following. S, and then S, I guess, dot weight, or we're going to pass an S, then 0. I guess we'll do that instead. So basically, we're going to pass every single vertex along with the weight. So S is going to be a starting node, basically. So S will have a weight of 0. And then we're going to have the following loop. So while PQ, or priority queue, is not empty, we do the following. This will be very similar to how breadth first search actually works. So we're going to just basically have the following. We're going to say U equals extract, all right, so better, extract min from PQ. So we're going to retrieve the smallest vertex weight, and we're going to sort it into U. And then we're going to basically just set, so actually it's not really going to be U, it's going to really extract the min, but I should have modified this a little bit. So let me just change this really quick. So it's going to really return sort of U, and then I'll call this weight. So it's going to retrieve the actual vertex name and the weight of that vertex. It retrieves those two basically. And then the first thing we'll do is we'll just say W at index U will equal that weight we just extracted from the priority queue a second ago. And write that into our array. And then have a loop right here, which will say for each neighbor, for each unprocessed neighbor, for each unprocessed neighbor V of U, we're going to basically sort of, I guess, relax this, which is actually kind of silly. I'll write this here. In the book it has it as relax. So we're going to relax basically U, V, and priority queue. So anyway, what does relax do? Well, it's going to reweight V potentially. So let's go ahead and write the relax sort of code out here as well, the function for relax. So what we're going to do is the following. So if V is not in the priority queue, then we're going to just simply we're going to, let's see, what's the actual technical term for this? I think I'm going to say just fine. I'm going to say insert. Let me just make sure I have it correct up here. Okay, I guess I'll insert. Basically going to insert V. And it's going to, basically the weight associated with V is going to be sort of U's weight, plus sort of the edge weight of UV, which is inserted into our priority queue. So I guess I should have maybe and comma, I guess PQ. We're going to insert this into our priority queue. We insert this vertex ID with this weight into the priority queue. So I guess the pseudocode from this MIT book is a little bit iffy, but I'll do an example and we'll definitely make more sense of it when I actually show an example of this. Now, if V is in the priority queue, so you have to actually maintain more data structures to be able to really know if it's actually in the priority queue. You don't want to have to linear search through the priority queue and see if V is there. So you're going to have some way. We have a pointer array that's going to automatically know which element in the binary min heap does V exist in. But we're going to just sort of, for now, magically just be able to, in constant time, know exactly where V is in our priority queue. So we would have to maintain some other structures in order to do this, but we'll worry about that not for right now, I guess. If it's already in our priority queue, we're going to go ahead and check the following. We're going to say, well, basically, if, it's an if, another if statement over here. So if sort of U dot weight plus edge weight of UV is less than V's weight. If you found a better weighted path to V, well, then we're going to have to basically update U's weight to just, oh sorry, V's weight, my mistake. V's weight to really just be U weight plus the edge weight of uv, and then of course we're going to then bubble up v. So relax basically means you're trying to find a better path from u to v, because there already could exist a path from our start node to v, and the whole point of relaxing is finding a better one. So here's, I guess, the picture that a professor, when I was his TA, he went over an example like this. Relaxation really means this basically. So we have pretty much u, then we have v, and maybe we have a different path. We found some other path, maybe through x, and it went through multiple nodes maybe. So this is going to not be a single edge, but a collection of edges, let's say. Let's say, you know, S goes not directly to U in one hop, but maybe it goes to multiple sort of paths. So a zigzag line means it has multiple nodes possibly. So the whole idea is, so far, our shortest path we had so far was this path, weight, plus this pathway was the best path from S to V. But now we found a better path. From S goes to U with maybe there's more than one possible node along that path. But then from U, there's a direct edge that goes from U to V. That's better than we've seen before. So we're going to update the weighted path from S to V that goes through U instead of through X. That's the whole idea. So that's what relaxation actually does, relaxing step. I don't know why it's called relaxed. I mean, I guess relaxed does a lot of work actually, it seems like. So it seems like it's almost counterintuitive or contradictory. How is this relaxing? It's doing work actually in this case, but it's actually known as relax. So let's go ahead now and go over an example of Dijkstra's algorithm. So I'm going to actually stop the video right here, write the example, and then continue to sort of save time with all of this. And all right, there is our graphs. I sort of did this in the meantime, so we kind of skipped ahead. So here we are. So right now we have the current graph, and right now it's going to be our W array. So I probably should have put that there. This will be our W array right there. So initially we have no shortest path constructed, and the first step is we're going to basically just go ahead and have our heap array, and it's going to contain S and then 0. So we're not going to actually maintain this array in actual heap order. We're just going to just have all the elements that are going to be in our heap, or just going to be, sorry, our PQ, I'll call it, just to be consistent with the pseudocode PQ. And we're going to basically run this algorithm. So the first step is, well, we have to run this while our PQ is not empty, and we can definitely see here we have our start node as 0 on our queue. So we're going to basically pop this off of our queue. So our first step is we're going to just basically pop S0 from our queue. And what's going to happen is, well, that means we can write this into our W array. I believe I already copied and pasted, this array, so I can just go ahead and just paste it right there. So I don't have to like redraw all of this. So we're going to write, actually I should have moved it a little bit more to the right, or to the left, sorry, because it's not really aligned. Yeah, good enough. So S will have the weight of 0. So we're going to write that into the array. Once you write it, we're never going to ever update this. So having a negative edge would actually, really we need to update more than once. But since we are a greedy algorithm, once we remove from our heap, we're never going to have to ever modify this node weight ever again. So weight will be 0, and then we're going to mark it in our, I'll put it here to help us sort of visualize. I'm going to put 0 right there, which means that's going to be the final weight of S. The next step is you're going to want to reweight all the neighbors and do that relaxation work. Okay, so one of S's neighbors will be A with the weight of 7. Sorry, that edge weight is going to be 7. So S's weight is 0 plus that edge weight 7 will give us a total of 7. And 7 is actually not, A is not in our heap. So you're going to go ahead and insert this node A with its weight into the heap. So the priority queue, the priority queue is going to contain A with the weight of 7. And the other neighbors of S, well, we have C as a neighbor. So we have a weight of 0 for S, plus the edge weight from S to C, which is 1. We're going to have a weight of 1 for C, so we're going to go ahead and insert C1 into our heap. And you can imagine that C1 would bubble up in front of A, but I'm not going to show all that, but you can just imagine it's going to do that. And the last neighbor of S is going to be D. So we're going to have, well, S has a weight of 0, plus that edge weight 5 will be a total of 5. And D is not in our heap, so we're going to simply insert it. So we're going to relax it by inserting it into our heap. So we're going to have D5 in our heap. That's going to be our first step. We first have to pop our start node S and then update all the neighbors and relax them all like that. Okay, so our heap is definitely not empty. We have 3 elements in our heap, so we have to continue this process. So very step by step. So greedy approaches are actually very simple to trace out on paper, which is actually kind of the benefit of this. So we're going to have to pop our priority queue. Our next smallest node weight is going to be C1. So we have to pop C1 off of our heap. So W array, we're going to update the W array by writing that value here. And there we go, like that. So S will be 0, C is going to be 1, and the rest for right now are going to be all infinity. In our priority queue, well, we just removed C1, so we're going to have A7 still in our priority queue, and D5. D5 obviously would have bubbled up to the front. That's our next smallest weight, but we're going to have to look at C1, and we're going to have to update all C1's neighbors. So C1 is now going to be written in red, which means that this is now officially processed. So we're never going to ever update C's weight ever again. There's no weight that's better from S to C than a weight of 1. If there was a better one, then we would have already processed it earlier. And also that implies you have a negative edge in your graph, which we know that Dijkstra's algorithm does not work with negative edges. So the fact that we popped C from the heap, that implies there cannot be a better path weight from S to C than 1 in this case. So now we have to go through all of C's neighbors. So what's our first neighbor for C? Well, A is a neighbor of C. So what's going to be A's weight right now? So A is 7 currently. Looking at C, well, we actually have a weight. So C has a weight of 1 plus that edge weight to A, which will be 3. So 1 plus 3 is 4. Well, we found a better weight to A, which will be 4. A better pathway we just found. So we have to go ahead and update this in our heap as well. We're going to update this to be 4. And then bubble it up, which in this case, it would bubble to the front. So we had to relax it. So we had to first look at A, and A was currently already in our heap. So we have to go ahead and update that element in our heap and then bubble it up. Now for C, we have a few more neighbors. We actually have one more neighbor. We have F is another neighbor. So F, well, we have C with the weight of 1 plus the edge weight from C to F, which will be 2. So grand total of 3. And F is not in our heap, so we're going to assign it to the weight 3 and then just insert it into our heap. So we're going to insert F3, which you can imagine this is going to bubble up to the very front. But we're not going to draw all that, but you can imagine for a binary min heap, F3 would have to bubble to the front. That's going to be our next step. Step 3. Well, we can see here our heap, or our priority queue, is definitely not empty. So we have to pop our next element, which looks like F3 is our next smallest element. Looking at our heap, the weight 3, which is F, is the smallest. We're going to pop F3 off the heap. And our W array is right here. And we're going to paste this right over there, like that. So S has 0, F will be 3, and C will still be 1. So W is going to be our final weight. So infinity really means right now we have not figured it out yet. And once you write a number into this array, we found our best possible path weight from S. So S to C is the best possible weight of 1, and S's path weight to F, the best possible weight is going to be 3. So that's all there is to it. Am I missing something here? Hold on. S0. Okay, we're fine. Okay. So now in our priority queue, well, we just popped F from the heap. So we're going to have A4 and D5 is in our heap. F3 has been removed. Let's go to our graph, and we're going to write this in red, implying that we have officially processed this node. Looking at F, well, it only has really just one outgoing neighbor. Actually, no, it has two outgoing neighbors. One to G and one to D. So G is not in our heap currently, so we're going to take F going to G. So F has the weight of 3, plus that weight to G will be 6, which will give us a total of 9. And then we're going to insert G with weight of 9 into our heap, because G is not in our heap at the moment. So we're going to insert G9. And you would bubble it up, but then obviously it would not bubble up because obviously it's the largest weight in our element, our set of elements right there. So we're done with that. And now F has a weight has a path to D. So currently D had a weight of 5, but look at this. F has a weight, has a path weight of 3 plus that edge weight of 1 from F to D, which will be 1 plus that 3, so 4. So I found a better pathway to D. So we have to relax D. So we found a better path. So whenever we insert into our heap or update something that's currently in our heap, that's a relaxation step. So we're going to update D5 to 4 and then bubble it up, which I guess it could go above the A or it could stay below because A is also 4 as well. And for F, there's no other outgoing neighbor, so we're not going to do anything else at the moment. Okay, so let's go ahead, and I'm going to close this set up. And once again, we're not done because our heap is definitely not empty. We have 3 elements in our heap, so we have to keep on running this algorithm. We only can stop once our heap is empty. The next step, we're going to pop the next smallest element off, and we have 2 elements that are both 4. So just to kind of break this tie, I'm going to pick the one with a smaller sort of letter. So A is before D in the alphabet, so I'm going to choose A because of that. Now, it doesn't really matter if I would have popped A or D, it makes no difference. I just chose A as a tiebreaker, but I could have chosen D instead, and it would not invalidate the algorithm. So just FYI. And then, of course, I pop A off of the heap. Good. And we'll have S is 0, C is still going to be 1, F is going to be 3, and A is going to be 4. So in our priority queue, A was popped, so we have now D4 and then G9. So going back to our example, A is now going to be red, so now 4 is now fixed. It's never going to ever update again. So we have only one, we actually have a few neighbors of A. So A goes to F, but we already processed F earlier. F is already, it's in our heap, but F has been processed. So we're not going to even look at that edge. We'll look at it, but then we see that this edge goes to F, so we're not going to do any relaxation, so we're done. Okay, so other neighbor we have of A is going to be B. So A has that node weight, that path weight from S to A, which is going to be 4, plus that edge weight of 1 to A to B. So B will have the weight of 5. And then what's going to happen is, since B is not in our heap, we're going to just simply insert B5 and then bubble it up, which in this case you can tell it would actually bubble in front of the G9 because 5 is less than 9. And I believe that's all we have for A. We have 2 neighbors. So that concludes that step. So again, we're not done because, well, our heap is not empty, so we can't finish this algorithm. So step 5, we're going to now pop D4. So in our weighted array, we're going to write it below. I'm going to go ahead and copy this to save some time. And we're going to have 0, 4, B will be infinity still, C will be 1, D will be now 4, E is infinity, F is 3, and G is infinity. And our priority queue will contain the following. It'll contain G9 and B5. In reality, B5 would be ahead of G9 in a priority queue, but you don't have to draw the actual the priority queues. Make sure we have our nodes in our priority queue, and we can very easily just sort of eyeball which element would get popped off next, because we know how min heaps actually work. So looking at D4 next, well, we're going to now write this in red because D has now been officially processed. We are now done. We can now write this in red. We're never going to ever update D to a smaller weight ever again. So now we're going to go ahead and try to reweight all of these neighbors. So D only has one outgoing neighbor, which is going to E. So E has the weight of, let's see, so D has a weight of 4, plus the edge weight from D to E is going to be 3, so it's going to be a total of 7. And since E is on our heap, we're going to take E7 and insert it into our heap. And it would bubble up, but obviously we can see here that B5 would be the first element, and then G9 and E7 would come after B5, obviously, but that's going to be the elements in our priority queue min heap. So step 6, we're going to have to pop an element off our heap again because our heap is not empty. So pop B5 off of our heap. Alrighty. So now we're going to write into our weighted array. We're going to write the following. So I'm going to just paste this. And S will have the weight of 0. A is 4. B will be now 5 from now on. C is 1. D is 4. E is infinity. F is 3. And G is also infinity. And our priority queue contains, for the moment, G9 and E7. We can imagine that E7 would be in front of G9, obviously, in this min heap. So now we're going to have to write B5. We're going to have to write this in stone because B5 has now been officially processed. We're never going to update B5 ever again. So looking at B in our graph. So B has one neighbor going to F, but F has been already processed. So we're not going to do anything with that. Then B goes to G. So right now, B has that path weight from S to B with the weight of 5. Plus the edge weight from B to G will be 2, so we have a 7 total. And G's current weight will be 9, so I found a better path weight to G. So I'm going to update. I'm going to go ahead and update this and relax it in my heap. So I would go ahead and look up G in my heap, update to 7, and then bubble it up. So as a relaxation, again, we're going to update G to a smaller amount because we found a better path weight. And then for B, there's nothing else we can do, so that's all we have left. That's going to be our current priority queue. And once again, we have two nodes of the same weight. So once again, there's actually, how shall we say, there is a tie once again. So we're going to have to pick the one that has the smaller, I mean, I guess we'll just pick them with a smaller alphabetical letter. So G, so I guess E is first, so sure, I'll pop E from the heap. it doesn't really matter which one I could have popped G or E, it would not matter. But I'll be consistent and pick the vertex with the smaller alphabetical letter. So E is before G in the alphabet. Yes, so A, B, C, D, E, F, G. Okay, perfect. So we're going to pop E off of our heap. All right. S has the weight 0, A is 4, B is 5, C is 1, D is 4, E will be 7, F is 3, and G will be infinity. And our priority queue currently has just G with 7. Let's go ahead and look at E. And E is now going to be sort of fixed. We're going to write this in red. We're going to update all of E's neighbors. So E goes to F, but we already processed F, so we're not going to have to do anything there, so leave it alone. And we can also go to G. So in this case, E has the path weight of 7, plus the edge weight from E to G will be 1, so 8, which is not less than G's 7, so we're not going to do any relaxation because we can't relax this vertex because we found a different path, but it's not a shorter or a more minimal weight path than we already have for G. So nothing happens here. So I guess that's all we can really do for E, so oh well. So our heap again is not empty, so we have to do some more work. Step 8, well, I guess we're going to pop G7 off of the heap. That's the only thing we have in our heap, so obviously that's going to be our next best path weight. I'm going to write 0, 4, 5, 1, 4, 7, 3, and then 7. Our priority queue currently will be empty. Let's see if we can add anything into our heap. So we're going to now have G as red, so now it's fixed at 7. And G has no neighbors. So I guess in this case we can't really insert anything else into our priority queue, so we are officially, that's it. We can't push anything else into our heap. And now our heap is officially empty. And then this is going to be our step-by-step process. So for your homework or an exam, so actually it's the same as what I do in 302, but I guess there is no other way to do Dijkstra. So whether we're in 302 or CS477, it's the same algorithm, nothing different in this case. So you want to, for homework or for exam, show these steps. So show the initial array, show which nodes popped off of the heap, and then update the weighted array at the very end. This will be our minimum weight. So this is going to basically tell us the minimum weight path from S to A, S to B, S to C, D, E, F, and G. This is not going to give us every possible pair. It's not going to give us the best path from B to C or B to D. No, only from S to A, S to B, and S to everything else. So that was our example using Dijkstra's algorithm. So let's go ahead now and go over the runtime, the proof that this will work, or at least go over like a kind of a proof by vigorous hand waving that this is going to work, and go over a few more other details involving Dijkstra's algorithm. Alright, so let's first go over the kind of a proof that this algorithm is going to actually find the best possible path from S to any node in our graph. Let's go ahead and zoom in on this. I can write notes out over here. So I guess the correctness, let's go over the correctness of Dijkstra's algorithm. Okay. So I guess one simple way of proving stuff in math is to use a proof by contradiction. So let's go ahead and for right now, so when we run this algorithm, Dijkstra's algorithm, we're going to of course always pop sort of a node along with its path weight from a starting node. Let's go ahead and just call this U, and I'll call it sort of W. Sure, so UW. So U is going to be the node name, and W will be the actual weight, the path weight from S to W, or to U, sorry, S to U. So, okay, so let's assume for right now, that W is not the minimal weight path from S to U. So if that's not the case, then I guess one issue is that then it had to have been a better path. This is actually kind of a little hand-wavy proof right now. So there had to have been a better path then from S. There had to have been a better path basically. So if this is the case, then there must be a better or a shorter, actually maybe a minimal weight path of weight W prime that is less than this W. That being the case, so if that is the case, then W prime, so the weight, then the weight W prime would have been popped off the heap at an earlier step of the algorithm. So because we assume that this algorithm does not work with negative edges, so assuming that there's no negative edges, then we can assume that, well, the W prime had to have been popped off the heap earlier. Therefore, U would have been processed with weight W prime and stored into the weighted array earlier, so W could have never been on the heap. So this is a contradiction. So therefore, this algorithm always works, because the idea is if a better path existed, it would have been found earlier. That's the idea. So I actually like using proof by contradiction because to me it's so much more natural. It's so easy to prove something with that. Induction is always hard because it feels like magic whenever induction is actually used. So that's the proof that this algorithm will always work. So basically, you show that you basically assume the opposite, assume it's not the best, and therefore, if that's not the best, well, then it would have been processed earlier, so therefore this could never have happened. I'm not sure it's like this in the book, but when I first learned about this algorithm way back when I was undergrad, the professor for the class explained it like this, and it made perfect sense to me. So I'm going to go ahead and just go back to my old undergraduate day notes and sort of have it like that. So the next step I want to do is I want to go over, well, why does negative edges not work with this algorithm? And it's because it's a greedy algorithm, that's the reason why. But let's go ahead and just sort of write this out. So explanation of why negative edges does not work for Dijkstra's algorithm. Okay. So it's pretty simple to show a very simple example. So, I mean, we could easily assume that it will work, and we can go ahead and just prove that it's not going to work. So that's kind of seems far-fetched. But anyway, let's go ahead and just sort of draw an example graph. Let's see here. Let's try the following. This is a simple enough graph. I'm going to use this. Let's go ahead and just... I'm discovering more and more cool features in OneNote every single day. So I definitely don't want to go back to using a whiteboard ever again. I think for one, a whiteboard always smudges all the time. This is actually way better than a whiteboard. So I definitely like this instead. Except that for some reason, on this computer it works, but on my other computers, however, OneNote, I can't sort of modify the pressure sensitivity with the pen. So on this home computer, it's set up where there's no pressure sensitivity, but on my other computers there is, and it makes it a bit harder to write. So I mean, I don't know how to fix that, but if you have any ideas, let me know. So anyway, we have the following graph, A, B, and C. And I guess A will be our starting node. So I'll just go ahead and I'll put an arrow over here as well as my starting node, starting from A. Awesome. Let's say we have the following. So we have, let's say, 1. Hold on. I think I'm going to try, okay, I'll try 2, 3. Oops, no. We're going to try 1. Okay, I'll try 2, 3, -2. There we go. Okay, so now I finally got my act together right there. So if we were to run this algorithm, Dijkstra's, what first happen, we have A with 0. And remember how it works, we're going to first have 3, and we're going to have 2. So we have C2 and B3 currently in my heap. So obviously we'd pop C2 off the heap, and this would now be officially processed. And C has no neighbors to go to. And then we're going to go ahead and pop B off of the heap. Actually, I could maybe, yeah, I'll keep it like this. So you can pop B off next, which will have the weight of 3. And B has a path from B to C with actually -2, which at total weight would actually be 1. So a better path exists from A to C. If you take A to B with a weight of 3, and then B to C -2 has a weight of 1, it's better than 2. So there's actually a better path, but Dijkstra's is not going to actually work because of the fact that it's greedy. Once it picks an edge or picks a node off the priority queue, we're done. We're not going to ever reprocess it again. So because of that, that's why it's not going to work. So here's a contradiction. Our proof is really just this example. So to prove that it always works, it's kind of harder to prove to show by contradiction or show by induction. But to disprove something is very simple. Just show an example, and that example is your proof that it will not work for negative edges. So only have to do is show one counterexample, and that's it. So disproving something is very simple, and proving something is always a bit more challenging. So there's that. Now, I want to also mention one more thing. What about negative cycles? Negative cycle does not work for any shortest path algorithm ever. Not for Dijkstra's. We'll cover hopefully Bellman-Ford later on. Maybe next week or so we'll start doing that. I hope next week. Basically, if a negative cycle is present in your graph, then there is no possible shortest path sort of algorithm. So a very big key note. If a negative cycle, now don't confuse it with negative edge, negative cycle, if a negative cycle cycle exists in the graph, then no minimum weight path can be constructed. And that's sort of, I think young people use like the period with a T at the end. This is that example. Period. I don't know. I just don't get it anymore. I'm getting old. I don't get the young people anymore. But I've seen people use that a few times here and there. So I googled that. I googled that on what's it, Urban Dictionary. I figured out, oh, it means like emphasizing something. So that's cool. I had to Google that, which means you can tell that I'm getting older. So anyway, that's a very big statement right there. So we can show with an example, once again, that this is actually the case. So we're going to have, oops, I'll use white pen over here. So it's just, I'll do the following graph over here. Yeah, I think this will be good enough. And then I'll also have two more shapes of this line over here. And then I'll have one more going over here. There we go. So I'll have, I guess I'll call it S, A, B, and C. So S has a weight of 2. Then we have 1, -3, -1, and let's see here. I think I'll choose -2, a bigger amount. Then I'll put 1. Okay, so right here we have a negative cycle. So I'm going to go ahead and mark these in red. Negative cycle is found right there. This is almost like going to school with a bicycle downhill and going back home downhill. So the idea here is there's no shortest path, because if I keep taking a cycle forever and ever, I'm going to have a weight of negative infinity. For A, B, C, and even for the shortest path to S is also going to be negative infinity, because we can take this path every single time, this cycle. If you go from S to A to B, B to C, and keep going taking that cycle a couple of times, and take that path from C to S at the end, it's going to be a smaller weight. Every time I take this cycle, we keep on gaining more energy. We get a better cost. It's almost like you drive the car more. As you drive in a special lane somewhere, let's say you have a special sort of street on somewhere here in Vegas, you take that sort of street, take that little cycle, and your car actually fills up with more gas as you take that cycle. I mean, that would be a pretty popular sort of area in Vegas if that was the case. So this is not going to work. There is no shortest path. I can take this cycle forever and ever and ever and keep getting a smaller overall path weight from S to A, S to B, S to C, and even S to itself for that matter. Why not? It's even going to be negative infinity also. I can take this path forever and get a better path from C back to S every time I take this sort of the cycle right there. So if a cycle exists, then there cannot be cannot be a minimum weight path at all. Negative edges, there can be a shortest path, but you cannot use Dijkstra's algorithm to compute that. Negative cycle means there is no algorithm that can construct a shortest path. So that's that. The last step now is to go over the runtime analysis of Dijkstra's algorithm, and I think then I might be sort of done. Let me go ahead and actually pause the video and go back so I know what time I have left. Okay, so after pausing it and counting my minutes, looks like I have about maybe 10 more minutes left, which I can end this a little earlier. So this will be the last thing I'll do is go over the runtime analysis, then we'll be done with this. And next time's class, we're going to go over Kruskal's minimum spanning tree algorithm. So that'll be next time. But let's go ahead and finish up the runtime analysis for Dijkstra's, and then we'll be done. So runtime analysis for Dijkstra's algorithm. Very simple. So basically all we're going to do is we're going to sort of, we run this out and we first have to pop, sort of have to pop a node off the heap. Well, actually, let me see if I can think of a better way of explaining this. Okay, so let's forget about the start node first. Let's go ahead and just assume start node is kind of obvious. What we first have to do is when we pop an element off, so actually I could have put this back on, my mistake. So you pop a node off the heap, we're going to relax or attempt to relax a neighbor, or relax all neighbors, my mistake, all neighbors, like that. So basically every attempt, we're going to have to look at an edge that goes to a neighbor and sort of and update or add to the min heap. So basically what's happening is we're going to look at every edge in our graph, and every edge we look at is going to cause us to have to insert into our heap. When we insert, afterwards we insert everything onto our heap, we have to pop an element off. So we're going to do this sort of work v number of times. So this is going to happen v times. And then what happens, well actually, well, and then we're going to basically, we're going to go ahead and insert everything into our heap one by one. So I think I'm going to, okay, I'll write it more the way that's more natural to me, so my mistake. So what's going to happen is, this is probably the way I would explain this instead. So every edge is processed, and then every edge that gets processed in the worst case causes us to update or insert into the min heap. This is kind of the way I would explain this proof. So every insertion will take log v time, because there's going to be at most v number of vertices in our priority queue. So the min heap will have at most v elements. So every look at an edge, every edge that gets looked at will take at most v step O of log v, actually, because every insertion takes log of number of elements in our priority queue. So every edge gets processed, it's going to force us to insert or update into our priority queue. Every insertion and update takes log of v time. So basically the runtime is going to be O of E log v, because every edge is looked at. So every edge will get looked at, just like for depth first search. Every edge is looked at, and every edge that gets processed is going to, in the worst case, cause us to insert or update in our priority queue, which will take at most log v times to reshuffle and bubble everything up in our structure. Now, sometimes they use O of E plus v. So sometimes you look at Wikipedia, it will give you this answer. Sorry, I'll write like this. There's a bit of an overkill because really it's because it's E if it's a dense graph, and then so this is really if it's dense we choose this. If it's sparse we choose this. So it's really just being very nitpicky about this. But really, no matter what though, it's gonna take E elements, E steps, number of edges you have in your graph. So really, we can just go ahead and just go with this. Now, I believe using a Fibonacci heap, you actually can get a better runtime in certain scenarios than E log V, because right now we're actually using a binary min heap. But it's not always going to be better using a Fibonacci heap. It can get better in certain circumstances due to its lazy insertion structure. But we're not going to really go over that. We're not going to just sort of, for now, use binary min heaps and just go over and just assume that every insertion is log V time. It's E log V. So it's going to basically conclude this videotaped Tuesday lecture. And that'll be it for right now. So next time we're going to cover Kruskal's minimum spanning tree algorithm. But until then, take care. Hopefully this video did help you. Thanks for watching, and till next time.